So this video is going to help you with Lab 7, the molecular geometry lab. So what we're doing for this lab is going through and starting with a compound name. You're supposed to fill in the chemical formula along with the valence electrons, then the Lewis dot diagram, which is the 2D diagram that we learned how to make during the lecture portion. Next, you have the geometry with electron pairs and without, bond angles, and then the polarity. And instead of polarity of bonds, I want you to do the polarity of the molecule as a whole. So if it's polar, you would write yes. If the molecule is nonpolar, you would write no. Now this last column here is, if we were doing this in class, what you would do is you would build this molecule using ball and stick models and then show me the model, and I would initial here. So for instance, the first example that we have that they did for you is ammonia. Ammonia's chemical formula is NH3. So to calculate the valence electrons of NH3, you make a list of each element present. So nitrogen and hydrogen. Then you write the number of atoms of each. So there's just one nitrogen atom in this molecular formula. You multiply that by the number of valence electrons. So for the valence electrons, you're looking at the periodic table. Now, since nitrogen is in group 15, it has 5 valence electrons. You then add that to the hydrogen atoms. There are 3 of them in this chemical formula. Each hydrogen atom has 1 valence electrons, so you get the total of 8. From there, you go putting the nitrogen in as the central atom, hydrogens around it, and make sure everyone's happy. To figure out the molecular geometry, you're using this handout here. And if you didn't get this handout, there's actually an appendix in the back of your lab manual that has this same handout. Okay, so you can find the molecular shapes and VSEPR handout in the back of your lab manual. So to figure out the molecular shape, you're going to do that based off of the Lewis structure. So you can see the 6 steps. The first one is drawing the Lewis structure, and that's what you're doing here. Next, you count the things around the central atom. And when we're talking about things, each atom counts as one thing, and lone pairs count as one thing. So what I have here is a total of 4 things around the nitrogen atom. 1, 2, 3, and then the lone pair is number 4. So to figure out the shape, I go to where the 4s are. So what I'm focusing on is this section right here. 4, 0, 4, 1, 4, 2, and 4, 3. So it's going to be one of these shapes. To figure out which shape, I have 4 total things, and then what comes after the comma is how many of those things are lone pairs. So 4, 0 would be 4 total things, but 0 lone pairs on the central atom. Well, for ammonia, I have 4 total things, but one of them's a lone pair. So we're looking at 4, 1. 4 total things, 1's a lone pair. So then my shape, when I draw it, would look just like this. But instead of putting dots as the atoms, I would write the actual atoms themselves. So nitrogen, and then the hydrogens. So in this first spot here, they ask you to include the lone pair when you draw the picture. But in the second spot, you're not supposed to include the lone pair. So that's the only difference between those two. Notice there's also a section that asks for bond angle. So the shape is trigonal pyramidal, And for the bond angle, you would just follow over and write the corresponding bond angle, in this case, less than 109.5. Now, is this molecule polar? So to figure out if it's polar or not, we did this in class. You could use the Lewis structure. So the rules for polar molecules. Rule number 1, if it has one or more lone pairs on the central atom, then yes, it is polar. Well, looking at this, whether you're looking at the Lewis structure or the electron pair geometry, notice there is a lone pair on the central atom. So since there is a lone pair on the central atom, yes, the molecule is polar. Another way to tell if a molecule is polar is if there's no lone pairs and the terminal atoms are not the same. And we'll be going through a few examples so that I can apply the rest of the rules. So the examples that I'm going to go through today are different than the ones in the lab, but they are going to be the same geometries as some of yours in the lab, and I'm trying to encompass all of them if I can. Before I move on from this one, actually, let me have a little ball and stick model here, show you what the geometry of that actually looks like, because some people had questions about how to know when there's a wedge and how to know when there's a dash. So I kind of wanted to show an example of that here. So this would be what ammonia looks like in 3D. So it's like a pyramid. Notice they're not all in the same plane. It's 3D. Some are sticking out, some are pointing back. So when we're looking at the drawing itself, this nitrogen atom here and this hydrogen, that represents this bond right here, the single bond. It's not a wedge, it's not a dashed line, it's just a solid straight line. That's indicating that this nitrogen and this hydrogen are in the same plane. Now for the wedge portion, so that wedged hydrogen, that is this hydrogen atom here. It is coming out of the plane of the paper, so it's indicated by a wedge. Now if I turn this slightly, you can see the other hydrogen. It's hiding back here. So it's represented with a dashed line because it's hiding. It's going into the plane. And you can't really see it unless you turn it at an angle. So since that hydrogen's hiding, we put a dashed line. So that's the reason for drawing it that way. All right. So let's look at another example. What I have next is sulfur dihydride. So I'm going to start by filling in all of these columns. The first column being the chemical formula. So sulfur dihydride, this is a covalent compound, which all our Lewis structures are, but we're also know it's covalent because of the prefixes, and this will help us figure out the molecular formula or the chemical formula. Same thing, different words. So sulfur is S. Since it doesn't say di, tri, tetra, I know there's only one. Now dihydride. So hydride is just the IDE version of hydrogen. And the di tells me that there's two. So that's how I'm going to come up with the chemical formula for sulfur dihydride. Now I need to calculate my number of valence electrons. And remember, to do that, we take the number of atoms and multiply it by the valence electrons that we find on the periodic table. So making a list of my elements, I have sulfur and I have hydrogen. How many sulfur atoms? Well, if there's no number after it, we assume it's just one. So there's one sulfur atom. For hydrogen, the subscript on hydrogen is 2, so that makes 2 hydrogen atoms. Next, let's fill in the valence electrons. So to figure out the valence electrons of sulfur, I'm going to look at the periodic table. And when you look at the periodic table, you'll see that sulfur is in group 16, right underneath oxygen. So everybody in group 16 has 6 valence electrons. They don't give you enough room to calculate all this, do they? Then hydrogen in group 1 has 1 valence electron. So this is going to give us a total. So 1 times 6 is 6, 2 times 1 is 2, add them together, 6 plus 2 gives me 8. So if I have 8 valence electrons, I need to know that number because when I draw the picture, the Lewis diagram, I need to know how many electrons I have to play with. So I'm going to start by putting sulfur as my central atom. It's the first, it's also the least electronegative, so that's how I know it's central. Hydrogen then, since there's 2 of them, will go on either side of the sulfur. The next step is to make sure your terminal atoms are happy first. Now, most of the atoms on the periodic table want a full octet. That's the octet rule, so they want 8 electrons. However, hydrogen and helium are exceptions to that. Hydrogen only wants 2 electrons. So since hydrogen only wants 2 electrons, the hydrogen atoms are happy as written because they each have a single bond. And a single bond is equal to 2 electrons. So this hydrogen has 2, and this hydrogen has 2. So the terminal atoms are happy. Next, you want to make sure that the central atom is happy. So to make the central atom happy, what we're going to do is make sure that sulfur has 8 total, because sulfur's not an exception, it wants a full octet. Now these 2 single bonds are being shared between hydrogen and the sulfur. So that means sulfur already has 2 electrons from this single bond and 2 electrons from that single bond. So sulfur has a total of 4 electrons right now. It wants 8. So to give it 8, what we're going to do is we're going to add a lone pair here and a lone pair here. Notice when we add electrons in Lewis structures, we always add them as a pair. Okay? If we just add one by itself, that's a radical. It's a very unstable structure. So we add them in pairs. So now this is the correct Lewis structure. How do I know that? Well, my hydrogens are happy, each with 2. My sulfur's happy because he has 2, 4, 6, 8. And if I look at my valence electron count, I've used all 8 valence electrons, no more and no less. So my next step is to figure out the shape. So first, the electron pair geometry. So to figure out the shape, we're going through those steps where we're counting the total things around the central atom. Now sulfur has 2 atoms around it, so 1 thing, 2 things. And it has 2 lone pairs. And remember, a lone pair counts as just 1 thing each. So this lone pair here counts as 1 thing, and this lone pair here also counts as 1 thing. So I have a total of 4 things around the central atom. So once again, I am looking in this section where the 4s. But now, after the comma, I need to look at how many of those 4 things are lone pairs. And in this case, we don't have 1 lone pair like we did up here, we have 2. So we're looking at 4, 2. 4 total things, 2 lone pairs. 2 of those things are lone pairs. So notice the shape we have now is the bent. So when I draw this, I'm going to draw it similar to what's here, but putting in the atoms themselves. So I would write sulfur, and then I'm going to bend it down instead of linear like it looks over here, so that my hydrogen's down here and my other hydrogen's down here. And since they want the lone pairs on this one, I'm going to draw a lone pair and a lone pair. So in this next picture here, I'm drawing the same exact thing. I'm just not putting the lone pairs there. To figure out the angle, so you're just following over. You already found out it was the 4, 2, that it was bent, and then it gives you the angle in the next column. And it's less than 109.5. Is it a polar molecule? Well, looking at our rules, if there is 1 or more lone pair on the central atom, then yes, it's a polar molecule. Do we have one or more lone pair on the central atom? We do. So my answer for that is going to be yes. And in case you wanted to see the shape, this is what it would look like in 3D. And it's bent, but all three atoms are in the same plane. That's why we don't have any dashes or wedges. So next, let's look at silicon tetrahydride. So kind of cut off the words a little there. So silicon tetrahydride. Silicon is Si. Hydride is, remember, just hydrogen. And to figure out how many, we're looking at the prefix. Tetra tells me there are 4. So now we count our valence electrons. So I have silicon and I have hydrogen. Number of atoms of silicon, I have 1. Number of atoms of hydrogen, remember we're looking at the subscript. There's a subscript of 4 on this hydrogen, so there's 4 atoms of hydrogen in that molecule. Then we're going to multiply by the valence electrons. Silicon it's in group 14, so it has 4. Hydrogen in group 1, so it has 1. So this is going to get us a total of 8 electrons once again. So when we go to draw the Lewis dot structure, silicon is our central atom, because we're never going to see hydrogen as the central atom in this course. So I would draw all 4 of those hydrogens with single bonds around the silicon. Next is to make sure your terminal atoms are happy first, and we said that hydrogens only want a single bond, and that makes them happy. They can only have 2 electrons. So my terminal atoms are happy. Now for the central atom, silicon wants 8. Well, looking at it, each of these single bonds represents 2 electrons. So it already has 8. And we've used all 8 electrons that we have to use. So this is the correct Lewis structure. So now when I go to draw the shape, once again, counting the total things around the central atom, we have 1, 2, 3, and 4. All of them are atoms. So we're looking at 4, 0 because there are 0 lone pairs on the central atom. So in this case, it's tetrahedral, and this is the shape here. It is a 3D shape with wedges and dashes. So draw it similar to this, but putting in the atoms themselves. So I would draw silicon, and then single bond hydrogen, a wedge with an H, and a dash with a H. Now your electron pair geometry and your molecular geometry are going to look exactly the same for these two because there are no lone pairs on the central atom. So if you wanted to see this in 3D, that's the tetrahedral. The white spheres are the hydrogens. So let me hold it this way. This hydrogen, this silicon, and this hydrogen here, these are all in the same plane. That's the hydrogen, solid line to the silicon, solid line to the hydrogen. This hydrogen here is pointing out towards us, so that's the wedge. And then the one hiding behind here, back here, if I held it that way, you wouldn't even be able to see it, right? That's the one with the dash. So looking at the bond angle, once again, just follow it over, and instead of less than, it is 109.5. Is this molecule polar or not? Well, one of our rules says that if there's no lone pairs on the central atom, which is what we have, no lone pairs on the central atom, and all the terminal atoms are the same, then it's nonpolar. So here, notice, all the terminal atoms are hydrogen. They're all the same. So this is nonpolar. So I'm going to write no for not polar. Next, let's look at the nitrate ion. So you do have some ions that you need to do in this lab as well. So to figure out what the nitrate ion looks like, the chemical formula, use your polyatomic tables. So the nitrate ion, I'm going to write it down here so I have more room to calculate the, oops, I believe it's a -1. So this is the chemical formula of the nitrate ion. Now you're doing the nitrite ion, so keep in mind it's different than nitrate. Nitrite is ITE. I'm doing the ATE one. So for nitrate, let's count our valence electrons. We have nitrogen, we have oxygen, and because of that negative charge, I'm also going to add one more electron. Because the reason it has a negative charge is because it has an extra electron. So once I get the total valence electrons from the nitrogens and the oxygens, I'm going to add an extra to that total because of that -1 charge. So for nitrogen, there is just one atom of nitrogen in the chemical formula. For oxygen, there are 3. Now looking at valence electrons, nitrogen has 5 because it's in group 15. Everybody in group 15 has 5. Oxygen has 6 because it's in group 16, and everybody in group 16 has 6. So multiplying across, we get 5 from the nitrogen, 18 from the oxygen, and then also we're going to add that extra one to our grand total. So what does that give us? 24? So we have 24 total valence electrons. So when I start drawing this, now it's time to draw the Lewis structure. Nitrogen's going to be my central. It's the least electronegative. Then I'm going to have my 3 oxygens around it. Next, I need to make the terminal atoms happy first. So this is the first time hydrogen's not our terminal. So oxygens, they're not exceptions to the octet rule. They want 8. So what we're going to do is go around and give everybody 6 more. Why 6 more? Because that single bond counts as 2. And if they want 8 and they already have 2, if I give them each 6, they'll be happy. So now all the oxygens are happy. Next, I need to make the central atom happy, but I need to see how many electrons I have left. So how many have I used so far? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. I've used them all. I have none left to put on the nitrogen. And nitrogen's not happy because he only has 3 single bonds for a total of 6 electrons. So if I have none left to put on him as an electron pair, what's my next step? I'm going to take a pair of electrons from one of the oxygens, doesn't matter which one, and I'm going to make a double bond. So what that's going to look like, there's a reason I used pencil here, and why you might want to as well, is now I'm going to have a double bond right here. This oxygen is going to have 2 lone pairs and a double bond, and the other 2 oxygens have a single bond and 3 lone pairs each. But notice now, if you count the electrons, everybody's happy. Each individual atom has 8, and we have only used the 24 that we had available to us. So I'm not done yet. This is the correct Lewis structure, but since it's an ion, you need to put brackets around the entire Lewis structure and put the charge on the outside. Because then when someone looks at it, they'll understand why you have an extra electron. Because if they did this count and didn't know that the overall molecule had a negative charge, they would be like, where'd they get that extra electron from? So that's why the brackets are needed. So this would be the correct Lewis structure, and now we go to figure out the shape. So let's count the things around nitrogen. I have 3 atoms around nitrogen. 1, 2, 3. Do I have any lone pairs on nitrogen? No, we didn't have any lone pairs to give him, so it's just the 3 atoms. So now we're looking at the 3 column. And the one we're going to choose is 3, 0, because we just said 3 total things, 0 of those things are lone pairs. They're all atoms. So here's the shape, trigonal planar. So Now I need to draw it. So to draw it, I'm going to put nitrogen, and this is the same thing. In this case, since there are no lone pairs on the central atom, both structures in both of these columns are going to look the same. Notice I'm keeping the brackets with the charge on the outside. And I'm drawing it so that it looks like a triangle, just like in the picture. Now for the bond angle, it says 120, so I'm going to fill that in. Now, is this a polar molecule? Well, just like in the previous example, there are no lone pairs on the central atom, and all the terminal atoms are the same, meaning no, it is nonpolar. I can make this structure for you quick. So we have 3 oxygens, one of them with a double bond. All right, so this is what that guy would look like. So I have single bond oxygen, and then notice the springs make this a double bond, but it puts it in the same plane as the other oxygen, so that's why it's planar. They're all in the same plane, all the atoms are. All right, so last but not least, let's look at oxygen gas. So oxygen gas. So we talked a little bit in class, in lecture, about 7 atoms that form diatomics in nature. And those were hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. So when I say oxygen gas, since it's one of those that forms a diatomic in nature, the chemical formula is O2. So diatomic means 2 atoms of oxygen combined. Di meaning 2. So to count the valence electrons for this guy, we have 2 oxygen atoms, 6 valence electrons each, so we have a total of 12 valence electrons. So I connect my oxygen atoms together. There is no central. I need to make the terminal atoms happy first, but there is no terminal, so I just pick one to make happy. So this oxygen now has 2, 4, 6, 8. Okay, well, I have 12 total, so I'm going to take, if I subtract 8 from this, that means I have 4 left. So I'm going to take my remaining 4 and put on this oxygen. But this poses a problem because one oxygen's happy with 8, the other only has 6. So to make this other guy happy, I'll take a lone pair and make a double bond. So let me erase that lone pair and put it as a double bond. So now both oxygen atoms are happy. Whenever you have a diatomic, doesn't matter which one of these, it's always going to be linear. In this case, it'll look just like that. You don't have to include the lone pairs. I'm not concerned about that. Bond angle of linear, always 180, straight across. Is it polar? Well, you could use your electronegativity tables to calculate it, but they're exactly the same atom, so their electronegativities are going to cancel each other out, making it nonpolar. So this should get you a start. You're going to be starting with water, which is very similar to sulfur dihydride, and then doing some ions, which I showed an example here of the nitrate ion. And then, of course, you do have some linear ones as well. Iodine gas is one of them. So when you do iodine gas, pay attention. It is a diatomic, so we're talking I2 when you do the iodine gas. So let me know if you have any questions.